When high-performance computing systems process highly repetitive data, they hit a predictable bottleneck. Every time a standard architecture re-ingests a block of data, even if it is completely identical to the previous batch, the CPU has to expend physical work to parse it. This graph shows ingest to searchable latency. The red line represents the standard baseline, requiring roughly 900 milliseconds of overhead to evaluate data. The blue Axiomark sidecar registers periodic processing spikes, but immediately drops to exactly 0 milliseconds for subsequent revisions. Under a standard bit-level evaluation model, a 0 millisecond overhead for data revision ingest is theoretically impossible. Even the most basic memory retrieval requires fractional clock cycles. That flat line is not a measurement error or a rounded fraction. It occurs because the system ceases physical evaluation entirely. It abandons logical data parsing and shifts to tracking physical state persistence. To understand how the system bypasses the CPU, we have to look at what happens to the data on arrival. Axiomark executes a process called a structural collapse, where multiple identical incoming data structures are merged. This illustrates the collapse of redundant text-based inputs. Instead of storing 16 separate logical blocks, the system funnels them into a single canonical physical state ledger. This achieves a strict 16:1 deduplication ratio, resulting in a 93.8% reduction in physical work. This schematic shows 16 repeating waveforms undergoing the exact same spatial collapse. The deduplication process is entirely agnostic to the data type. Eliminating spatial waste with a 16:1 ratio is only the first step. The 0 millisecond temporal latency is achieved by maintaining that single canonical state over time without ever waking the CPU to re-verify it. Instead of hashing text structures repeatedly, Axiomark pays the computational cost of canonicalization exactly once. It maps the incoming data into a stable physical proxy. This oscilloscope readout tracks the state vector, breaking data into 5 thermodynamic components: amplitude, timbre, theta, bits per quanta, and spectral class. Regardless of diversity, these vectors normalize every input into a strict 0 to 1 range, establishing absolute dimensional consistency. Once the vector is established, any identical subsequent inputs are treated as mere logical references to this single established state. Mapping discrete data into thermodynamic vectors converts an intensive, continuous text parsing problem into a highly efficient physics evaluation. With the spatial problem solved, the engineering challenge shifts to the temporal axis. The system must determine exactly how long a persistent state can be trusted before the CPU is required to arbitrate. This plot maps the effective persistence curve. Decay over time is calculated as e to the negative delta t over tau. This establishes a corridor of legitimacy. Data remaining below the 0.10 threshold is accepted as a stable continuation. A continuation ruling means the hardware can bypass the central processor entirely. Calculating these vector residuals within the secure corridor on the GPU is the precise mechanical reason the system achieves those 0 millisecond latency flatlines. However, processing real-world operational workloads over long sequences exposes a flaw with relying on a purely static threshold. Over thousands of cycles, the system is susceptible to entropic drift. This is a slow, accumulated creep in the data's timbre channel. It is not an actual structural break, but rather harmless system noise. This graph tracks a signal as it slowly drifts upward. Left unchecked, this harmless noise eventually breaches the 0.10 threshold boundary, triggering a false positive novelty alert. The operational penalty for this false positive is massive. It forces an unnecessary CPU arbitration wake to investigate the noise, instantly destroying the zero latency streak. Defending the zero latency streak requires a mechanism that can distinguish between slow, harmless entropic drift and a genuine structural break. This vulnerability was resolved in the Round 11 revision with the dual-threshold IDST drift channel. This plot visualizes the adaptive tracking equation. It generates a dynamic reference line that curves to stay parallel beneath the drifting signal. By evaluating against a severe anchor displacement bound, an actual structural break appears as an immediate vertical deviation. This dual rule allows the GPU to silently absorb slow drift without dropping its guard against lethal data shifts. The IDST drift channel perfectly isolates structural truth from ambient noise, securing the continuous GPU hold. Let's return to this ingest to searchable latency benchmark and map the physics concepts directly to the operational data. Those 0-millisecond valleys are the result of the GPU successfully holding the corridor of legitimacy via the IDST drift channel. The periodic latency spikes at revisions 3, 6, and 9 indicate true structural novelty, forcing the CPU to cleanly arbitrate the new state. Axiomark doesn't eliminate computing work. It simply ensures that physical work is never paid twice for identical structural states. By abandoning binary string tracking for thermodynamic state vectors, architects can transform data repetition from a processing bottleneck into a continuous near-zero latency advantage.